Hi class, so at the end of the last video, we saw how we could solve for an optimal strategy that would maximize our expected value regardless of what strategy our opponent was using. What I'd like to do today is just go through more examples of solving for the optimal strategy for two-player games, and also show how we can solve for player 2's optimal strategy along with player 1's optimal strategy. So I'd like to take a look at the example of the batter going up against the pitcher again. So here we go, we had the batter versus a pitcher. And what did the game matrix look like? Well, the batter could guess fastball or curveball, and the pitcher could throw fastball or curveball. And if the batter guessed correctly, then they would have a higher batting average. If they guessed incorrectly, they would have a lower batting average. Remember, batter was player 1, and the pitcher's player 2. So I've left the names off of the matrix, but we know where they belong. And so let's go ahead and solve for the optimal strategy. Okay, so remember, how did we do that? Well, first we put in probabilities for which the batter would guess fastball and curveball, but we let this be a variable and we called it P. So let the P be the probability that we'll be guessing fastball, and 1 minus P be the probability that we're going to be guessing curveball. So P is the probability we're going to be in the first row, and 1 minus P is the probability we'll be in the second row. Now, remember, we had to calculate expected values based on what the pitcher did. We don't have any way of knowing what the pitcher is going to do, so we calculated the expected value versus the pitcher throwing fastball. I'll just abbreviate this EV sub F because it's the expected value versus fastball. And we wanted the expected value versus the pitcher throwing curveball, which I'll abbreviate similarly EV sub C. The point is that when we're in the fastball, these are our two outcomes. When in the curveball case, these are our two outcomes. So what's the expected value versus a fastball? Well, I have a probability of P that I'm going to be having 0.300, and I have a probability of 1 minus P that I'm going to be getting 0.100. And I want to add those together, so I'll have in total P 0.300 plus 1 minus P 0.100. So let's move that down here. P times 0.300 plus 1 minus P 0.100. And now we just need to simplify. So let's expand. Just remember that we should distribute over here. So we have 0.300P plus 0.100 minus 0.100P. So in total, this is all equal to 0.200P plus 0.100. Or, just for sake of simplicity, I don't need to write all those zeros. It's just traditional with batting averages. So 0.2P plus 0.1. Now let's find the formula for the expected value versus a curveball. Now we're in this case where the payoffs are given by the curveball column. So I have a probability of P of getting 0.200 and probability of 1 minus P of getting 0.500. So my expected value is going to be those two added up. So I have 0.2P plus 0.5 minus 0.5P. So it looks like I'll have negative 0.3P plus 0.5. Now what I'd like to do is I'd like to visualize these two expected value formulas as lines. And we'll talk about why in a second. But let's just graph these as lines. So here, on the y-axis, I'll have expected value. And on the x-axis, I'll have my probability, p. But remember, p is the probability I'm choosing fastball. Now, okay, so let's graph the expected value versus fastball. We'll graph that in green. So it starts, the y-intercept is at 0.1. Just label some tick marks here. And so it will start there. And where will it go? Well, the probability ranges from 0 to 1. And what happens when I plug in 1? If I plug in 1, I'll get 0.2 times 1 plus 0.1. That's just 0.3. So the point I should plot above 1 is 0.3. And this is a straight line, right? It's of the form mx plus b. So this is our expected value line against fastballs. And it makes sense that this line is sloped upwards, because what this is saying is that the more often I guess fastball, the higher my expected value will be against the pitcher throwing a fastball. And that just makes sense, because I'm trying to guess correctly. So if I guess fastball more often, I'll do better when the pitcher throws a fastball. Let's look at the expected value for the curveball line. So it has a y-intercept of 0.5. And when I plug in 1, I get negative 0.3 plus 0.5. That's just equal to 0.2. So we'll go to 0.2 down here. And the line's going to slope downwards against a straight line. This is my expected value versus a curveball. Okay, and so why does this make sense? Well, the more I guess a fastball is coming, the worse I'm going to do against a curveball. So you see, when I never guess that the fastball is coming, that's when I'm at probability 0. That means I'm guessing it's a curveball instead, right? Then I have the highest chance of hitting a curveball. And when I guess that there's a fastball coming, I'm going to have the lowest chance of hitting a curveball. Okay, and the idea is that along the way, right, I could have a new mixed strategy, right? What if I go halfway in between? So if I choose p equals 1/2, this corresponds to the mixed strategy of guessing fastball half the time, which implies that I'll be guessing curveball for the other half the time. Now, how's that going to do versus a fastball versus a curveball? Well, it's going to do okay versus a fastball and okay versus a curveball. You see that I'm not doing as well as if I had just guessed it was a curveball versus a curveball, right? Because sometimes I'm going to guess a fastball and it's going to throw a curveball, so I'm doing less well. But I'm going to do better against when the fastball is actually thrown, right? Because I'm guessing fastball more often than not. This is what I was talking about last class, where we're saying we're sort of hedging our bets. Okay, we're not going to have as extreme of a difference between what happens when we guess when the pitcher actually throws a curveball versus a fastball. Now the difference between those is much smaller. Okay, so, well, what are the actual expected values? Well, remember, I can just plug these into my expected value formulas. So EVF, what was the formula here? It was 0.2p plus 0.1. Let's see what happens when I sub in p equals 1/2. Gives me 0.2 times 1/2 plus 0.1 simplifies to 0.2, or 200. So I'll have a 200 batting average against a fastball, and against a curveball, the formula was negative 0.3p plus 0.5. If I plug in my mixed strategy of p equals 1/2, I'm going to get negative 0.3 times 1/2 plus 0.5. And what's that going to be? Negative 0.150 plus 0.500. Looks like I'm going to have a 0.350 average against a curveball. Okay. And those might seem pretty good. In particular, batting average of 350 versus a curveball is great. Batting average of 200 versus a fastball is not so great, but it could be worse. But what I'd like to point out is we have no control whether or not the pitcher is throwing a fastball or a curveball. And if they catch on that half the time we're swinging as if it were a fastball and half the time we're swinging as if it's a curveball, then they can choose to always throw fastballs. And so we've looked at the expected value versus their two strategies, but they can always put us in our worst case scenario. So even though we could get 0.350 against a curveball, we probably won't bat so high because they can just make sure that they're always throwing fastballs at us. So they can always guarantee us the lowest value between the two. This is where the idea of the optimal strategy is counteracting what they can do. So remember, what was the idea of the optimal strategy? We were trying to find where these two lines actually intersect. We were solving the equation EV against fastball equals EV against curveball. And so what point on the graph is that? It's actually this point right here. We're saying that our expected value will be the same regardless of what pitch comes. And so let's go ahead and solve that. We have 0.2p plus 0.1 equals negative 0.3p plus 0.5. Add 3p to both sides, and we'll subtract 0.1 from both sides. And finally, we'll divide by 0.5. Turns out that p should be 4/5 or 0.80. What this is saying is that the p value for where these intersect is 4/5. That's the intersection point. So our optimal strategy then is to guess fastball 80% of the time, or with probability p equals 0.8. They mean the same thing. Again, because what's going to happen if we do that, then it doesn't matter if a fastball or a curveball comes, we're going to have the same exact batting average. The pitcher can't choose to throw the pitch that we're going to hit less because we're hitting both of these pitches with the same average. So our optimal strategy is given by the probability of guessing each pitch. Now, what's our actual batting average going to be? Well, that's just going to be the expected value at which these two lines actually intersect. And so how can we find that out? How can we solve for that? Well, we have the formulas for our expected values, and we have the probability that we'd like to guess, and so it's as simple as just plugging in this value back into either one of these equations. Notice that both equations will work because they're equal to each other at this p-value. So let's try 0.2 times 0.8 plus 0.1. This is equal to 0.16 plus 0.1. That's equal to 0.26. And I'll write 260. So we're getting a batting average of 260. let's just see that it really is the same no matter which one we plug into. Here, I'll get negative 0.24 plus 0.5, and again, I'm getting 260. This is a good place where you can check your work because you solved when they were equal, so you really should get the same batting average. And what is this saying? This is saying that our optimal strategy, we can expect a batting average of 260. And that's a pretty good batting average. If you have a batting average of 260 overall, then you're definitely making the team. But more importantly, and again, I've stressed this so many times, the whole point is that it doesn't matter what the pitcher throws at us. We're going to be able to get this batting average. This is the expected value of our strategy. Okay, so we've walked through how we can use this payoff matrix to find an optimal strategy for the batter. But you might also be wondering, well, okay, the batter will do at least 260. You might be asking yourself, what can the pitcher do to make sure the batter's batting average is as low as possible? We found a strategy for player 1, but does player 2 have another strategy? Let's not call it the best strategy, let's call it the optimal strategy because that's what we defined it to be. Okay, so let's redraw the game matrix. Fastball, curveball, fastball, curveball. Remember, this is the batter here. I'm going to write these in just because it'll help us not be confused later. The pitcher is just choosing between these two columns. Okay. So what are the pitcher's strategies? Okay, so the pitcher can choose between throwing a fastball and throwing a curveball. But just like the batter couldn't know what the pitcher was going to throw, the pitcher doesn't know what the batter is going to throw. So they're not sure, are we going to be in the fastball case or are we going to be in the curveball case? So let's say the pitcher throws a fastball 50% of the time and a curveball 50% of the time. We'll notice that the probabilities then for the first column will be half, the second column will be half. Here I'm writing the probabilities below the matrix because it's a probability for each column. It's not a probability for each row like it was for player 1. And now we can walk through all those steps that we did before, but remember, eventually what we did is we just kept these probabilities as variables, p and 1 minus p. But in fact, just so we're not confused between player 1 and player 2 strategies, I'm going to call these probabilities q and 1 minus q. So q is the probability that the pitcher will throw a fastball. Before p was the probability that the batter would guess a fastball. Now, how are we going to find out what the best probability is? Well, just like before, we need to test it versus the batter's 2 strategies. So we want the expected value versus the batter guessing fastball. And I'm going to abbreviate this again, EV versus F. Now don't be confused, I did EVF before, but that was for player 1. This is a different EVF. And the expected value versus the batter guessing curveball. Just like before, I'll abbreviate this, EV versus C. Now how do I do this? Well, it's just like before, but now everything has switched from rows to columns. If the batter guesses a fastball, then we will be in this first row. And so our 2 outcomes will be 0.300 or 0.200. And The probability with which they'll occur is q and 1 minus q. So what's the expected value going to be? Well, it's going to be probability q times that outcome of 300 plus probability of 1 minus q times the outcome of 0.200. And so what does that equal? Again, let's just distribute and simplify. This is 0.300q plus 0.200 minus 0.200q simplifies to 0.1q plus 0.2. So my expected value against the fastball is given by that formula. Now what about against a curveball? Well, let's switch our outcomes. The batter is going to guess that it's going to be a curveball. And so what are our payouts going to be? They're going to change from 0.3 and 0.2 to just 0.1 and 0.5. Again, the probabilities remain the same. 0.1q plus 0.5 minus 0.5q simplifies to minus 0.4q plus 0.5. Now we can graph these again. I'll plot the expected value on the y-axis, and on the x-axis I'll plot q, the probability. I should say the pitcher, throws a fastball. So again, the probability can only range between 0 and 1. If we plot out these lines, this first one will start at 0.2. That's the y-intercept. And it'll go up by 0.1, so it'll wind up at 0.3. You can also get that by just plugging q equals 1 into there. This is the expected value. So this is the expected value line against a fastball. What about the curveball? The curveball starts at 0.5 and will go down by 0.4. So by plugging q equals 1, I'll get 0.1. So the expected value against a curveball, as against them guessing a curveball, is given by that line. Here's EVC and EVF. Now, what's the optimal strategy going to be? It's going to be exactly where those lines cross. And so to get the actual strategy, I want to find the probability where these two lines cross. And to get the batting average, I'm going to want to find the expected value at this point. You don't need to graph these every time, but I find that the visualization helps me understand what's going on a little bit better. I'm solving for the intersection point of these lines, which means I want to set them equal to each other. EVF equals EVC. And now I'll just substitute their formulas and I'll solve. Add 0.4q to both sides. And subtract 0.2 from both sides. Looks like I'm getting q is going to be 0.3 divided by 0.5, or 3/5, which in this case is going to be 0.6. Now what does that mean? It means that the q value where these intersect is 0.6. So our optimal strategy, the pitcher's optimal strategy, is throwing a fastball with probability 0.6, or 60% of the time. Now, what's the expected value? That is the batting average they can expect to keep the batter at. This strategy will ensure that the batter has a batting average of Now, how do I find that out? Well, remember, I just plug this back into either one of these equations. It's probably easier to plug it into the EVF equation. 0.1 times 0.6 plus 0.2. That's just 0.06 plus 0.2, which is 0.260. Well, that shouldn't be a surprise, because that was the best the batter could do themselves with their optimal strategy. So it turns out that the pitcher's optimal strategy and the batter's optimal strategy is going to yield the same expected value. And so the pitcher can guarantee a batting average of at most 0.260, and the batter can guarantee a batting average of at least 0.260. And so this is why solving for optimal strategies like this is telling us the value of the game, because it's the score that both players can guarantee. So this is the value of the game. Since both players can use a mixed strategy to guarantee this outcome. Notice that their mixed strategies were different, right? If we look at the probability for which the pitcher was throwing a fastball, it was only 60%, while how often should the batter have been guessing a fastball? The batter should be guessing a fastball 80% of the time. So P and Q are really different. Each player has a different optimal strategy, but they'll lead to the same expected value. Let's summarize all of this. Batter's optimal strategy: guess fastball 80% of the time, and guess curveball the other 20%. What was the pitcher's optimal strategy? Well, throw a fastball 60% of the time and throw a curveball 40% of the time. And what's the expected outcome, or the expected value? Well, it was the batting average of 260. Great. So we can see now kind of how powerful this sort of analysis is. I can tell you exactly how you should be guessing pitches and throwing pitches just based on a couple statistics about how well a batter hits fastballs and hits curveballs. This, of course, can be applied to any sort of total conflict zero-sum game, and we'll see that in the worksheet. Again, I know that this material is getting a little bit tricky, so please take your time to go through this material. Don't be afraid to rewatch videos, rewatch sections to just see me explain it again. And if you have any questions, please don't hesitate to send me an email and ask. Come to class and ask a question about the worksheet. Whatever you need to help understand this. All right, take care.